This is part 7 in a series of videos in which I'm attempting to repair this MADAS mechanical calculator. In the previous video I overhauled the motor and it's been on test for a while. It's running fine, the brushes are almost completely bedded in. Still running it, as you can see it's running fine. Running it at reduced voltage, it's currently around 140 volts instead of 240. And that's simply because there's no load on it and series wound, so it will just go as fast as it can depending on the voltage that's supplied. And if I put any higher voltage on, then the mechanical brake starts to engage, so I don't want to do that, it will just burn out the shoes. So it's running at this speed. This is probably the speed it would run at in the machine. I haven't refitted the greases yet, I simply topped up the two holes, or at least put some oil in them to make sure the bearings are running properly. And you can see one of the brush holders through the opening in the motor. I'll just turn the light off and you can see that there's almost no arcing at all, which is exactly what we're looking for, and that will probably disappear completely by the time the brushes have fully bedded in. So this is now starting to work fine. I'll get this out of the way, and the next thing I want to do is work on the actual mechanical drive between the motor and the calculator. Slight difficulty in doing that because you can't attach the motor to the calculator unless you put everything back in the case. I will leave the front panel off the calculator so we can still see inside and hopefully do any work we need to. But the next thing I need to do is get the motor out of the way, get the case on the bench, and see if we can figure out what to do about replacing the missing gear. Okay, I've got the case back on the bench. As you can see, I've given it a really good clean inside and out, and it's come up quite nice. The inside was absolutely filthy. It was probably 1/4 of an inch deep in grease and grime, so that took some cleaning. And the next thing I need to do is to fit the calculator mechanism back into this case so that we can figure out what size gear we need to use for the missing gear. Now I can't measure it as it is. There's no way to get these two parts to mate up without using the case, and it's a bit unfortunate. It makes it quite difficult to work on from this point, but next step is to get the mechanism back in here. Now the way it's held in, it drops in, and then there are pins like this that slide in through a couple of holes in the front of the mechanism. There's another matching hole at the back, goes through that, through the case, and then the end of this bolt screws into a boss on the enclosure, and there's one of those at either end of the case. Now when I got this calculator, there's only one fitted. The one at this end was fitted, but the one at the motor drive end was missing, and I suspect that's possibly why the machine was damaged and the belt broken, because when you take this pin out, this whole end of the mechanism drops down and then this gear hits the case, and you can see there's a big gouge in the case here, and that's possibly what banged up the machine and caused the belt to break. So the problem is I only had one of these bolts, and you can see they are not standard bolts, they're kind of a weird custom design. So needless to say, the only option I had was to make a replacement, which is what I've done. So I've made a replacement bolt, and the only real tricky bit in doing this was in trying to determine what the thread pitch and size was. It's obviously a very old machine, so quite often threads are weird sizes. Also, it's almost certainly imperial, and my lathe is metric, so cutting imperial threads on it is a bit of a pain. But eventually I figured out what the thread size was, and what I do is just by way of testing before I make the full size component, is I make a little stub up, make sure that it fits and screws into the thread as it should do, and that fits fine. So I made this in brass. This one's steel, but I made it in brass. I prefer brass look and feel on old machines like this, so I made this one out of brass, but you could just as easily make these in steel. And this fits in through an opening underneath this mechanism. So if I can find the hole, this one slides up through here, slides into place through the mechanism, and then screws into this boss at the top, and the mechanism then rests on this this bolt. So I'll get the calculator dropped back in, refit both bolts, and then we'll see how well this fits together, and we can start looking at the missing drive gear. Okay, I've got the calculator back into its case. I fitted both of the supporting bolts. We've got one here and one on the far end, and the calculator is now firmly held in place, and more importantly, the gear is now free to spin. As I say, without this bolt in, this gear rests on the case, and I need to have the bolt screwed all the way in. There's also a shoulder on the bolt that pulls the calculator up into position when it's screwed all the way in, and so of course we need that in to know what the final position of this gear will be. But now the whole thing's held securely in place. The carriage is free to slides very nicely and freely, and the next thing is to look at replacing the missing gear. So I'll zoom the camera in, we'll have a look at this, and I'll just explain how I'm going to go about doing this. So our next task is to try and make up a replacement for the missing gear, and so step one is to try and figure out what we need. So the drive comes in here onto this pulley via a flat belt, a leather belt, and it goes through this gearbox. It's a 5-to-1 reduction gearbox, and then that causes the calculator to rotate. Now this gear was missing when I got the calculator, so that's the one we have to make, but the first step is to try and figure out what sort of gear it is. I can quite easily machine one if I need to, but the first thing is to try and figure out what the tooth profile is. It'll be one of two basic types. It's either going to be cycloidal or involute. Now cycloidal is mainly used on things like clocks where very low friction is required, but on machines that run at speed such as this, it's far more likely that it's going to be an involute gear, and looking at the teeth, they do appear to be involute gears. So the next step is to try and figure out what size gear we need. Now it could be a custom gear. I've seen machines of this age where it's not either type of gear, it's just kind of somebody's machined a random type of gear and it doesn't follow any particular pattern. So first thing is, it looks like an involute gear, so we'll work on that basis to start with. Next thing we have to do is figure out what size and what pitch gear this is. If you're not familiar with gears, if you know about gears, then you might want to skip this part, but if you're not familiar with gears, there are some fairly simple ways to determine exactly what's going on and what size gear it is and how to machine these. It's going to bring a bit more light in so we can see more clearly what we're doing. Okay, hopefully you can see that a bit better. So there's various ways you can measure gears, and what I tend to do is make the assumption it's a modulus gear, and as I say, if you're not familiar with gears, then there are various mathematical formulas that determine the size and pitch of the teeth on the gears, and a very simple rule of thumb, we'll start by measuring the pitch. Now the pitch is the point pretty much halfway up the tooth. That's the pressure point of the tooth. So you probably can't see exactly what I'm doing here, but I'm measuring between the face of one tooth and the face of the next tooth along, and I'm doing this at the point roughly halfway up the tooth. Try and be as accurate as we can with this. So it's about there. So that's the approximate pitch of these gear teeth. So that looks like it's about 3.18, 3.17 millimeters. The nearest matching modulus size to this would be 3.14 or pi, and that will give us a modulus 1 gear. So if we make the assumption here that it's a modulus 1 gear, we can confirm this. We need to measure the actual pitch, radius or diameter of the gear. And again, an easy way of doing this is to measure the distance between the inner part of the gear, so that's the inner radius. So here we're getting 29.5, so if you remember that, and then outside 34. So if we find a difference between that, we got 34 minus 29.5, and if we divide that by 2, that gives us 2.25. So if you remember 2.25, and if we subtract if we add 2.25 to 29.5, that gives us roughly, because this is a fairly rough measurement I'm doing here, a rough measurement of the diameter at the pitch point of this gear. So it's around 31.75 millimeters. If this is a modulus 1 gear, then it will have the number of teeth that is equal to its diameter. That's the pressure pitch point diameter in millimeters. And the nearest whole number, it's going to be a whole number of course, we're not going to get fractions of teeth. So the nearest whole number is 32. So in theory this gear should have 32 teeth. So I've marked one of the teeth to make it easy to count. So if we start counting here, 1, 2, 3, 4, 5, 6, 29, 30, 31, 32. So indeed it does have 32 teeth. So that would tend to indicate that this is a modulus 1 gear, and this particular gear has 32 teeth. What we need to do is figure out what size gear goes on here. Now it obviously will also have to be a modulus 1 gear, otherwise it wouldn't mesh with this one. So all we need to do is measure between the center point of the gear, that's the center point of its rotational axis, and the pressure radius that that gear will use. So in other words, the point from the center of this axle to halfway up the tooth on this gear. If we then double that and look at that value in millimeters, that will tell us how many teeth need to be on this gear. Just to clarify this, if you are interested, this works on any modulus gear as long as you understand the general thinking behind it. So I've got another gear here. This is another modulus gear, and I'll do the same thing with this. It's actually stamped on this gear what it is, but if we want to figure it out, if we take the outer diameter, so it's 25.5, and the inner, so that's the minor radius, minor diameter, so that's 22.5. So 25.5, 22.5 is 3. So if we divide that by 2, it's 1.5. If we add 1.5 to 22.5, then that gives us 24. So the diameter at the pitch point for this gear is 24 millimeters. So that's at this point. And I know that this gear has 30 teeth because I counted them. So if we now divide 24, which is the diameter, by 30, so 24 divided by 30, so 24 is the diameter in millimeters and 30 is the number of teeth, that gives us 0.8. So in theory this should be a 0.8 modulus gear. And although you probably can't see it, if I look on the gear, it's stamped on it 0.8. So that is a modulus 0.8 gear, 30 teeth, and that works for all modulus gears. So you can work out the size of gears, the number of teeth, their diameter. So what I need to do here is figure out what we have to replace this gear with. And so if I take a rough measurement, and luckily it will be a whole number, so we only need to be accurate to a certain point, but we need to be fairly close. Okay, so that's coming out at 11. So if we double that, we get 22, and so that tells us that we need a 22 tooth modulus 1 gear. And just measure the thickness so we know how thick a gear we're aiming for. So it's 5.4 millimeters. So we're looking for a 22 tooth modulus 1 gear that is 5.4 millimeters thick. And so what I'm going to do is, rather than jump straight in and machine one in brass, what I'm going to do is actually 3D print one, so we can just put it on here. It'd be much easier and quicker than machining one out of brass. And if that fits, then of course I can go ahead and machine, or maybe even be able to find one off the shelf. It does have a bit of a strange center section, so I doubt we'll find a gear off the shelf with a square central hole. But if I 3D print one first, just to confirm what we think this is, and if that fits, then we know that we're on the right track and we can go ahead and machine a proper replacement. Okay, so if I got my measurements right, we should have a gear that will fit quite tightly onto this center boss and engage properly with the calculator drive gear. It's only PLA, so it won't withstand full speed operation of this machine, but it will prove if we've got the right size gear, and we can then go ahead and machine a brass one. So I'll try and fit this on. It's going to be quite a tight fit. I made it very slightly over tight. Indeed, it does fit on very nice and tightly. So don't have the center screw yet. I need to find out what size that needs to be, but we don't need to fit that on just yet. Certainly the meshing looks good. There's very slight amount of free play, so there's probably about 1/1000 of an inch backlash, which is exactly what it should be, and in theory this should now turn nice and freely, which it does. So that is indeed the right sized gear. So I'm just feeling for any tight spots or binding just to make sure that it is right, but no, that's actually the right size. Okay, so now we know what size gear we have to machine, and it's if you're interested, it's an M1 22 tooth 5.4 millimeter thick gear. Okay, so that's looking fine, and the next step is to machine a metal version of this. But before I do that, I need to look at reattaching the motor, so I'll get this out of the way and we'll look at the motor mounting bracket and see what work we have to do to that. So this is the bracket that the motor bolts on. The motor bolts on the back of it, and this section protrudes underneath the calculator, and there's an opening in the bottom of the calculator case that allows a contact to poke through, and when you push the big plunger on the calculator to start the calculation, it shorts out these two contacts. Now this has been modified at some point, and I've discussed this with the owner of the machine, and we're going to return this to the original configuration. These shouldn't be here. These should actually be on the switch that sits in this location, and I'm assuming that they were moved down here because the switch was lost. The problem with them being here is that there's mains goes directly into this, and so by applying mains here, then even if the switch is turned off, you still have mains going into the inside of the calculator and through these wires, so it's obviously not ideal, not particularly safe, so we want to return this to a more standard mode of operation. And the owner did find this switch, and it is actually the right type of switch for this application. It sits up here, so it goes on this way round, and these two power input prongs should be coming out of these holes. And because of the way the switch is arranged internally, I'll just take the cap off, you can see that if the power comes into the top here, then effectively there is no power applied to the machine at all unless the switch is on. And when it's turned off, power is broken here, disconnected, and so power is only on these two pins, which is exactly what you want. You don't want power going around the machine it's kind of semi-automatic, and also the way this was wired up, and the switch was wired across these contacts. So what would have happened is when the switch was turned on, the motor would have run irrespective of the position of the plunger. That may be well what caused the damage in the machine in the first place, that the motor was turned on when the calculator was in a mode that it's not supposed to be running. That's what the little thumb wheel's for on the side of the calculator. It's meant to allow you to manually drive the machine to get the plunger to start to operate. So by wiring this in properly, then it should protect the calculator and also make it more authentic as well. Now the problem I've got is, although it's the right type of switch, it's not the right one. It's the right size, but the mounting holes are further apart on this. Unfortunately, they're not quite far enough apart to clear the holes that are already in the bracket, and I can't reorientate the switch because it would then be the wrong way up. The prongs have to come out the back. That's the way the original configuration was. So what I'm going to have to do is fill these holes. So I'll put in some threaded inserts, cut them off flush, and I'll bond those in so they're not going to move, and then I can re-drill this bracket and tap it with holes slightly further out, and that will enable me to reattach this switch. And then once I've done that, I can replace the wiring. This needs replacing. It's very badly damaged. All the insulation's flaking off, and I can also get it wired in properly, so it's wired the way it's supposed to be, and then move these prongs back onto the back of the switch. So quite a lot of work to do on here. I'll do that in the next video. That's it for this one. Any comments welcome. If you do have one of these, then please let me know.